the other borehole. The signal that we get is an electric field. Then we move the receiver to other locations to measure the signal, and also later we move the transmitter. And the purpose is to get a dense ray coverage of the plane between the boreholes, which is necessary to apply a tomography inversion of the distribution of the electromagnetic properties of the plane. What we measure, the signal, is affected by the electrical properties of the medium, and the dielectric properties that affect the wave propagation are the dielectric permittivity, which is related to the electromagnetic velocity of the wave, which lithologically it is related to the soil water content. The second parameter that we can get the distribution of and the wave propagation is affected by is the electrical conductivity, which is related to the electromagnetic attenuation. And lithologically, it is related to clay content and to salinity of water, if there is, in the soil. I said, yeah, also to the water. I mentioned water related to the permittivity, but the water, if the water is desalinated and you don't have solutes, so theoretically you don't have. Usually we do have some salinity in the water. Yeah. So when we do a tomography inversion with GPR data, the conventional methods use the data for the inversion, either the first arrival of all the signals, which by this data we can get tomography inversion of the velocities, which relate to the permittivities, or either the first cycle amplitude of the data, from which we can get an attenuation inversion. This is inexpensive. This is very fast inversion to get a distribution of the parameters, but it gets not such good resolution. In the full waveform inversion, we use the all waveform data. So this is the signals that we see, in order to, and we fit this waveform data to get a better resolution. What we see here is the all waveform from that are measured at receiver at all depths from a single transmitter in that location. And in the full waveform, we try to simulate exactly all this data in order to get the parameter models of the plane. Using the waveform inversion, we can get detailed sub-wavelengths, which the wavelengths that we usually work in our cases are 1 meter, so we can get sub-meter resolution. But this inversion is very expensive computationally, and we need a supercomputer. Another big advantage in full waveform inversion that unlike the ray base, which I get either the attenuation or the permittivity, we get in the full waveform inversion 2 models, both of the permittivity and the conductivity. So the motivation for this study, so in order to protect and manage groundwater, we need a detailed knowledge of the flow and transport processes, which controls the migration of fluid particles and solutes. So, the tracer velocity and the tracer spreading, they strongly depend on the heterogeneity of the aquifer. Tracer experiments that monitor the tracer plumes can be used to determine the transport characteristics. What we see here at the top is a characterization by ray-based GPR. The colors are facies. The brown is sand, and the blue is gravel. And this is by GPR full waveform inversion. What I'm emphasizing on is that the characterization by full waveform inversion could explain splitting by a tracer test in red arrows that was applied in the aquifer before previously to this characterization. And the characterization in the full waveform inversion is better than the ray-based. We want now in this experiment to apply time-lapse monitoring in order to monitor the tracer using GPR full waveform inversion. That will be the first time that time-lapse full waveform inversion is done, is monitoring a tracer test. Yeah, and we want to study the potential of GPR full waveform inversion to monitor and map the plume in tracer tests using different types of tracer. So just a general overview on geophysical modeling, geophysical inverse modeling, and specifically full waveform inversion. So we have the data that we measure, the electric field. What also we need to begin the inversion is the subsurface starting models. Here are starting models that we use, and we need to be somewhat close to the real models. Otherwise, the optimization will not go to the right direction. And we also need the effective source wavelet that is emitted from the transmitter. This can be done in the waveform approach using deconvolution based on the data that we measure at the field and the starting model. We can iteratively estimate the effective source wavelet, which is then used in the full waveform inversion. This is a necessity for the full waveform inversion because then it restricts the inversion only for the models and not for the source, which at this point is already estimated and known. Using a forward modeling of the electromagnetic propagation by Maxwell equation, we can get the model data. And we can calculate the data misfit between the observed and the model data. The observed and the model data are waveforms. These are some of the waveforms that we have. So here in blue, I'm showing the real data. And in red, this is the simulated data that we get from the starting model. Iteratively, if the convergence of the inversion has not yet fulfilled, the models are being updated. Forward modeling is reproducing simulated data until the data misfit and other criteria are being fulfilled, and we get the final models, both of permittivity and the conductivity. And here, if we started with this kind of starting model, this may be one of our final models, which are the distributions of the permittivity and the electrical conductivity. Then, based on this geophysical properties, using petrophysical relations, we can convert each of these properties into the tracer concentrations. Just very briefly about the computationally part of the inversion. So the data misfit is basically the difference between the simulated and the observed fields. For each cell in the model, we get the gradient direction of both the permittivity and the conductivity. And then at each of the cell, we have an update of both the permittivity and the conductivity. This how at the end we get this more detailed distribution of the parameters. And then we choose the final model based on a good fit between the observed and the model traces, and that the changes are low enough. And then we get we think that these are the best results. So the strategy for our study is first to apply a synthetic tracer test, which is monitored by synthetic GPR full waveform inversion. We test 3 types of tracer. One is positive electrical conductivity, which mimics saltwater tracer. The second is negative conductivity, which mimics deionized water. And also we wanted to test liquids that affect the permittivity, and we used an ethanol tracer, which its permittivity is lower than of the groundwater, and it also changes the conductivity, and that's a tracer that we'll test synthetically. And after, and if we're happy with the synthetic results, we tested it in an experimental field tracer test where we used saltwater tracer. So to the numerical study. So in order to prepare ourselves for the aquifer that we will work in, we used previous data of the heterogeneity of the hydrological and the dielectric parameters of the aquifer in order to generate realistic aquifer models, from which we run flow and transport model to get the spatiotemporal fields of the concentration in the aquifer. Yeah. Then this concentration are converted to dielectric properties, which we then run the wave propagation. We get the synthetic data and we calculate the full waveform inversion models. So here are some examples. So this is the background. Here we have a distribution of the conductivity only, because when we add salt, we don't expect change in the permittivity, but only in the conductivity. This is the background, and this is if we have desalinated water, which decrease the conductivity. First, we look at the GPR data. What we see here are the electrical field. Each horizontal line is a waveform measured at a receiver at a specific depth. And we see an increase in the amplitude when the electrical conductivity was decreased in the desalinated water. This is what we expect. And now we see the electrical conductivity full waveform inversion results, and we can see that the structure is generally regenerated or recovered, and also for the deionized water. If we look at the data, we can see that the data of the full waveform inversion fits very well the observed data, and we see that the difference data is almost nothing. So the fit is very good, and we are getting pretty good recovery of the aquifer model due to the deionized water. This is a test of a positive and very high electrical conductivity tracer. Here we see that the data, especially at the bottom part, is almost is decreased a lot because of the high electrical conductivity. we see that at the full waveform inversion that now the recovery is not as good. We can see here a region without a tracer traveling, but the full waveform inversion did not recover it as well. It's in general okay, but we found that as higher the conductivity, the signal is lower, as we see, and the full waveform inversion results are less accurate. Also, we see that the difference between the observed and the model data is less good than when the conductivity is lower.
The frequency is 100 megahertz?
We use the 200 megahertz.
Not 1 meter.
The wavelengths?
You said in the beginning that your wavelength is 1 meter.
About.
About,
that's the general order. Okay. So now I'm testing the ethanol tracer, which provides negative contrast comparing to the background. Negative contrast in both permittivity and conductivity. So here we have the permittivity background and the permittivity time lapse. On day 15, we see decrease in permittivity and also decrease in conductivity. And these are the full waveform inversion results. These are, again, the background of permittivity and conductivity. And these are the time-lapse day measurements. And again, we see quite good recovery. Then by these results, we can get the tracer. Here we have the aquifer models, but we want the tracer changes in permittivity and conductivity. Also, we see the effect of the ethanol on the data. Here in green and red, these are the true and the full waveform inversion of the background. And when we added the ethanol, which decreased the permittivity, which made it faster velocity, so we see earlier arrival and also lower conductivity, which means lower attenuation and higher signal. So this is the tracer concentration recovery, which we can get by physical relations. From the background, we can estimate the distribution of the formation factor from the full waveform inversion conductivity. And after we estimate the formation factor in the time-lapse, we can use the time-lapse conductivity model in order to estimate the distribution of the tracer concentration. If I just stop it once, anyway, we can see that the recovery is pretty good, and the scale of the resolution is indeed in the decimeter scale, even goes to 20 or 30 centimeters. Okay, optimistic from these promising results. We went to do the experimental saltwater tracer test, monitored by GPR full waveform inversion in time-lapse. The host test site for our experiment was Quothausen test site in Germany. This is a gravelly sand aquifer, very heterogeneous in hydraulic conductivity, and we applied it in saturated conditions. We injected a saltwater tracer through this borehole of 8 meters water column all over the borehole. The conductivity, electrical conductivity, was 1200 millisiemens per meter, where the groundwater conductivity was 90. So it's like 13 times higher electrical conductivity. And once the tracer was injected to the aquifer, it was transported by natural flow conditions of about, in average, 1 meter per day. Then for 14 days, we measured the GPR crossfall data between the black lines that we can see. The main planes that we will look at are the ones in flow direction. This one from the injection to the one here on 38, and also this one, and also perpendicular to the flow direction. Also, we measured electrical conductivity of the water in the boreholes. So we have this monitoring boreholes that we can get some validation that our results from the geophysics are valid. The GPR data, we followed conventional GPR processing and also full waveform inversion pre-processing that we can see we adapted from the literature. So the full waveform results. So on the left side, we see the background before we injected the tracer. These are the starting models, and these are the full waveform inversion results of the permittivity and of the conductivity. Then this is an example of one of the time-lapse measurements on day 3 on that borehole from the injection to the first borehole. And these are the permittivity and the conductivity results. We can see that the permittivity results of the time-lapse and the background are very, very similar. Well, we don't really expect changes, and that proves it. And about the conductivity, we can see an increase in electrical conductivity. We see much of it at the bottom, also at some other places here. And that is what we expect because the salt water increased the electrical conductivity. Then to calculate the tracer conductivity from the static full waveform inversion electrical conductivity, we calculated the formation factor distribution. And using the formation factor and the time-lapse electrical conductivity, we could derive the tracer conductivity itself. And these images are what we are interested because that gives us an estimation of the tracer conductivity. Now look at the experimental results, experimental data, not related to the full waveform inversion, just the GPR. Here we look at the background. These are waveforms when the antenna was at this depth. This is in day 2 and in day 14. What we see in day 2, when the salt water was in that plane, we see a decrease in the signal of the data due to the attenuation by the salt. While on the last day of measurements, on day 14, we can see almost a full recovery that the signal was recovered to the background values. Now, looking at the data from the final full waveform inversion, we can see from the difference between the measured and the full waveform inversion data, we can see that the difference is pretty low, whilst it was the highest at the day when the salt water was in the plane, which again, the signal to noise ratio was low, and that's made the fit a bit worse. Yeah, and again, what we can see is that even from the GPR data, we see that the most of the intrusion is below 8 meters. We can compare it with the background and the last day. So we see most of the tracer was traveling at the bottom. I mentioned it at the beginning that we can estimate the effective source wavelet. The effective source wavelet of the transmitter is unknown, and it is necessary for an accurate full waveform inversion models. We found that there is an effect of the salt water on the antenna source. So in the injection borehole 29, we can see that at the first days the electrical conductivity was very high, and until about day 4 or about day 4 it returned to the background levels. What we found after we estimated the effective source wavelet, that we saw an apparent shift on these days, and also we can see it in the spectrum that the central frequency of the spectrum was shifted to lower frequencies, and also the magnitude is lower when the salt is in the plane. So these wavelets are the ones used for in the full waveform inversion. If we would have a constant source wavelet that we measured at the background, it would affect our accuracy of the full waveform inversion results.
Can you explain why this is happening? The antenna size doesn't change.
Yeah.
What causes the wave?
There is a coupling between the antenna and the electrical conductivity that of the salt water that traveling through the borehole near the antenna emission location. And this coupling between them, they have a mutual effect that changes the spectrum. Also, you can see that the spectrum here, the central frequency is about 70 megahertz, when before I said it was 200 megahertz. This is also just the effect of the water. If we measure it in air, it will be closer to 200. Okay.
The electrical conductivity decays more of the higher frequency, shifting to lower.
Yeah, it reduces, and the absorption or the attenuation is mainly, it's dispersive. It's mainly on the higher frequencies. So we have a higher loss in the higher frequency. All right, so let's look at the tracer conductivity. Tracer conductivity for now on this plane, on the injection plane. We can see that the intrusion or infiltration inside the planes is happening through discrete locations, and we can see continuity on the same location at different days. This is strengthens our reliability of that results. We can also see a decrease in the conductivity, and that's due to spreading and dilution with the groundwater. We see that at the bottom part, the velocity is higher than at the higher part. Yeah, and that's we see that we can refine the perforation passes in the decimeter scale. So this is very high resolution that we haven't seen in other methods like ERT, which is very common for monitoring saltwater tracer test. Yeah, so this I mentioned. Most of the mass is below 8 meters. Now let's look at other planes a bit further away. This is the continuity. So we can see that at day 7, most of the tracer has arrived this part of the aquifer. We can see pretty nice continuity. Each plane was inverted individually. So if we see continuity, is a good sign for our results. This again, a few more days later, we see a continuing decreasing of the tracer conductivity, as we expect because of the spreading. And just as a validation for our full waveform inversion results, this is a breakthrough curve that we measured at this borehole, 10-meter distance. We have the breakthrough at around day 8, which is pretty much in agreement. This is the same borehole, and we see here about the maximum at day 7, and at day 9 it's already been lower. So this strengthens our results of our tracer conductivity in that borehole. Now I'm looking at this plane perpendicular to the flow direction. This is day by day tracer conductivity recovery. Again, we see pretty good continuity between neighboring planes. We see that the tracer conductivity comes to the maximum at about day 5. And that's in agreement with what we expect of 1 meter per day, because this plane is a 5 meter distance from the injection borehole. And later we see a decrease somewhat in the conductivity.
Can I ask you, Peleg?
Yeah.
What was the vertical distance of the lapse of the moving of the transmitter and receiver?
Yeah. So what we do is we keep the transmitter fixed, and we move the receiver. Yeah, the receiver. Yeah. So the receiver we move every 10 centimeters.
Okay.
And the transmitter depends, sometimes 20 or 40 centimeters. So the differences are larger between the transmitter, but we do it reciprocally.
I understand. So 20 or 40 centimeters. Yeah. Does it somehow relate to the layering? You see, it's very anisotropic. What is the characteristic thickness of layers we see in the lab?
Yeah, you mean anisotropy in
what we see is a huge anisotropy.
Yeah, we know that we know from grain size and from other penetration tests that we know there is variability at the scale of.
I'm asking, your distance of the, let's say, receiver moving is about 30 centimeters.
No, receiver 10.
Receiver 10
centimeters.
Transmitter
Yeah.
I cannot see the depth. What is the characteristic depth of a layer? Yeah. What's the total depth?
Okay.
Asking if this pattern is an artifact,
yeah.
or is this really the layering of the soil?
Okay. So
it's 10 meters?
We know from characterization. Here I'm showing the tracer.
The depth is 10 meters?
Yeah,
yes,
this is 10, this is 4, okay?
Here
we see about 7 meters, okay? What we know from the characterization, that also from GPR full waveform inversion, and also from penetration, we know that the correlation length is at the vertical, is at the scale of 20 centimeters. Okay, so we expect a lot of heterogeneity. And what we see is the tracer. This is a good question, if what we see here is real. Yeah. What strengthens it is that we see continuity, also spatially and temporally. That we see, we know that the direction from before. We know the direction where it should go. We know we should be some dilution. Also, another way to somehow see the validity of the results. This is a previous facies model. In yellow, this is sand. Turquoise is gravelly sand, and blue is gravel. And what we see from our tracer results that most of the plume traveled at the bottom, below 8 meters, which is in agreement with this model. Also, using this tracer time-lapse results, we can get breakthrough curves at some specific locations. So here I just put 2 locations, and we see that at the higher part, we see an increase in conductivity until day 10 with much lower conductivity, and that's in the sand region where we know that the hydraulic conductivity is lower. Whilst in the gravel area, we see much earlier breakthrough curve, and the conductivity is much higher. So these are results from the full waveform inversion recovery, and this is from previous characterization of hydraulic conductivity. So this is another strengthening of our tracer recovery results. And also, we measured every day electrical conductivity profile in the water in the borehole. So we moved slowly the sensor in order to get the conductivity profile. And we see, for example, at this borehole, which is this borehole on some day, we see that increased electrical conductivity below about 8 meters. And this is where we expect most of our mass. But we couldn't get very good fine structures in the borehole because whilst we moved the radar, it mixed the water. So this is kind of a rough way to kind of validate our results from the full waveform inversion. Yeah. And we also want to compare results that we got from my monitoring with GPR full waveform inversion to the very common method of ERT monitoring. In the same test site, there was a saltwater tracer test in the past, which recovered the electrical conductivity in ERT, and this is for my experiment with GPR full waveform inversion. This is not a complete, most accurate comparison, just because the injection from at each of the experiments was different. So they injected from here, and I injected here. So the magnitude of the conductivity will not be similar, and we shouldn't compare it. Just the size of the structures that we recover. So from ERT, they also recovered most of the tracer mass traveling at the bottom of the aquifer, but we cannot see structures below the meter scale. Whilst in my monitoring, I could recover heterogeneity at the decimeter scale, and we still need to find ways to test that what we see is actually true, and this is a good question. So we did the borehole, but based on the aquifer past results, we have a good not every. So for example, just this borehole is this one, and this is in the main flow, whilst this borehole at the side, and we see increased conductivity here. So this part we trust less, because in our borehole conductivity results, we did not have it. So in our future results, future studies, we should put a lot of focus on high repeatability. We find high repeatability of the location of the sensors, yeah. But about the main parts that show continuity in space and in time, we are pretty confident with, for example, for this part and others that I showed before. So to conclude, we applied first a synthetic tracer test that monitored GPR full waveform inversion, and we test different types of tracer, which change both the permittivity and electrical conductivity. And we, for the first time, we applied a saltwater tracer test monitored by GPR full waveform inversion. We found an unprecedented resolution at the decimeter scale, which showed better recovery of preferential passes than any other geophysical method. The model GPR data fitted very well the observed data. The GPR full waveform inversion also can provide us heterogeneous high-resolution petrophysical relations as we estimate from the electrical conductivity deformation factor and from the permittivity. In saturated conditions, we can get the porosity. And these static parameters can help us estimate later tracer parameters distribution. We found that in waveform approach, the effective source wavelet allows to retrieve the full waveform inversion results independently from the borehole filling effects, and this is very important when the tracer penetrates through the borehole and is getting coupled with the antenna. And tracer heterogeneity from our study agrees with the knowledge from previous studies in the same test site. Now, just I put together, if it works. Okay. Here I'm showing, all the results together. Okay, not this time. Okay. Anyways, that was my study, and I thank you for your attention, and I'm open for any questions. Thank you.
If you can show just the stills, the first and last, no?
Yeah, I don't know why it doesn't give me the option now. Can. I will show you later, surely.
So, expectedly, you've shown that the system is limited when you have high electrical conductivity because the signal dissipates and you get low signal-to-noise ratio. And my thought was, how about if you change the GPR frequency in the simulation? Can you somehow compensate for that? I understand that the resolution will also change.
Yeah.
But you will get better signal-to-noise ratio.
So yeah, once the signal-to-noise ratio is at some threshold too low, the fit of the data will not be as good. As you said, when we work with lower frequencies, the attenuation is lower, but the resolution is also worse. So what you said is true, yeah. But we could, in that way, we will resolve larger, coarser structures.
But can you find an optimum where you will get a better fit?
Yeah, I mean, in synthetic studies, you can add your tracer conductivity, and then you can test different antennas in your forward model. Yeah. That's right.
First of all, very impressive, really, the resolution and the methodology. I recall that when Danny or and I were thinking how to invert a simple TDR waveform, it's like a Stone Age methods compared to what we do today. Okay. I also apologize for mentioning the dependence of the permittivity on water content. In the first slide, I didn't know that it's all water saturated. And now I have a question. The most strong characteristics of your profiles is the anisotropy more than the heterogenic. Now, as I know, at least for TDR, when the wave propagates along a waveguide, that both the velocity and the attenuation of the amplitude when the wave propagates in a given direction depends on the electrical conductivity and permittivity on the perpendicular direction. It's a transverse wave, right? If it propagates this way, it's the permittivity this way and the electrical conductivity. Now, after your interpretation, you show a very anisotropic profile, which means that the permittivity and the conductivity are very different. Your wave are mostly horizontal or sometimes maybe more vertical, but let's say when it is the horizontal, receiver and transmitter at the same day, and your anisotropy is, the layer is very horizontal, question is, this is for another PhD, not for you. Maybe after to do another iteration, if you receive interpreted a field which is anisotropic, maybe to do another iteration and to account for this anisotropy in the inversion. Because I understand that you refer to isotropic permittivity and conductivity, right?
Oh, the results that I received.
No, but your inversion for a single ray in your physics propagates in an isotropic medium, right? Isotropic.
No. So if you look before, למה זה לא זז?
לא, זה לא. זה כל הכיוונים, אבל עדיין, זה כיוון נמצא.
Okay, it doesn't move, but I will explain it. So we get the models have heterogeneous distribution of the permittivity and the conductivity. At each iteration,
for a single inversion, when for the inversion, you take into account the whole field of the permittivity and conductivity.
Sure. Each iteration, both the permittivity distribution and the conductivity distribution change. We have emissions again from all the transmitters in the modeling, of all the transmitters, which now consider the updated permittivity and conductivity. And we have Maxwell equation, which simulates the waveform, the wave equation. Yes, so if we have anisotropy, which sees, say, a high permittivity between low permittivity at both sides, we have a waveguide, and we see it in the simulated data, and we see structures of waveguides. We see because it's a waveform forward model, it accounts for all these effects.
For the macroscopic anisotropy, okay, I get it. It does not account for local anisotropy, right? Locally it's isotropy. Each point, yes.
Each cell is isotropic, yeah. But each cell is the size.
I understand. So I'm not, I'm not a mathematician.
Okay.
But is it that true that this anisotropy, it's not something that you artificially convert? You say it's
no.
You testing it.
The anisotropy is being created through the inversion process, iteratively inversion process. Just the optimization that tries to fit the model data with the observed data, and the algorithm that looks for the gradient direction of the parameters at each cell, and then updates the parameter at each cell. It brings this. Yeah. So
in your forward model, the numerical model element, each element has permittivity and conductivity.
Yeah.
And you optimize those for the entire model.
Yeah.
And all the cells in each.
Yeah, each cell. You have 5 meters. Each cell is about 10 centimeters. So you have the width is about 50 cells. The height is about 80 cells, and 4,000 cells. Each of them, it's updates at every iteration. Usually, full waveform inversion, 20 to 30 iterations. We calculate it on a very strong supercomputer. But then it takes 10 minutes on a supercomputer.
But no, it's a little bit suspicious. My last let's say your effective frequency, let's say about 100 megahertz, about. So it's about 3 meters in vacuum. Your permittivity about 20. So it's 50, 60 centimeters wavelength, order of half a meter, right?
Okay, I didn't really follow the calculation now, but no, it's more. I think it's more than a meter. It's more than a meter.
No, if it's 100 megahertz, it's 100 megahertz.
Yeah.
It's 3 meters in vacuum.
Okay.
By the velocity of light.
Okay.
If it goes with the square root of the permittivity is 25.
Yeah.
So it is short by 5.
Yeah.
So it's 60 centimeters, 50 centimeters.
Okay.
Order of magnitude.
Okay.
Now, what is your layering?
We see
Also 50
to the
centimeters.
even lower. We see 20.
Okay, it's not that far away. That's a little bit.
Okay.
I think when they use it, they have to use it in several cross sections in other media, and see that it's not repeatable. This characteristic 10 centimeters, which is the wavelength. Understand what they say? If they repeat it in other scales with the same frequency,
He's asking if the layering might be an effect of
the wave. Okay, but
yeah, because we have dense coverage, it's we see finer structures due to the inversion than what is expected solely from the physical resolution or the physical wavelengths, or you would say quarter of a wavelengths. We can see, yeah, Danny.
Yeah, some technical issue. He said the natural EC of this aquifer 90 microseconds per centimeter.
Per meter.
Of the groundwater, 90, not of the aquifer. The bulk aquifer has lower properties. Yeah. The groundwater was 90 millisiemens.
I'm talking about the water. Yeah. 90. So like we have here our aquifer 40 meters below here. We have the well.
It was meters per meter. It was what we gave the numbers. It wasn't per centimeters. It was millisiemens per meter.
Yeah.
What?
Millisiemens per meter. 90 millisiemens per meter. It's equal to 900 microsiemens per centimeter. If you are used to that.
Okay.
I was also a bit.
And we have 800. No,
okay.
I'm asking. I thought it's a much fresher water than we usually have in our Mediterranean climate. So I would think. Okay. So here we usually we do it work like to trace fresh water, rainwater, salinated water, which are in the area of 200 millisiemens per centimeter, 100. Like if you would have done not the tracer would not be 10 times more saline, but 10 times less saline. Would get
first of all, you ask in saturated conditions.
Yeah.
Saturated conditions. I was showing in the synthetic test that it's possible. Yeah.
but only better.
No. Okay. Any more questions?
Thank you.
Okay.
Okay, thank you.
Thank you. אלעזר.